Welcome to session 4 in our series on electricity and magnetism. In session 3, we ran electricity through this green wire, so copper wire with green insulation, and as the electrons moved through the wire, it produced a magnetic field around the wire, and that magnetic field interacted with these magnets and rotated them. Now, we're going to do a brief version of that, like that. We'll do that again, but we're going to do it while we're measuring how much electricity is being consumed. And then after we do that, we're going to take a look at how could we make electricity more effective in doing mechanical work. Okay, so let's get started. Now, if we're going to measure something, we need to think about, well, what is it we're going to measure? Well, the parameters that define what's going on with dynamic electricity is, one is the voltage, the other is the amperage. So we've got volts times amps, and the product of those two equals watts, the unit of power. Okay? Remember, this already is a rate. It's not an amount of energy, it's how quickly the energy is being produced, transmitted, and used. It's a rate, okay? So let's go over each of these other two terms. You're probably familiar with them, but we'll just do a quick review. The voltage is the ability to push the charges through our circuit. Our circuit has certain things in it that consume the voltage that we provide. One of them is electrical friction. We call that resistance in the electrical engineering world. So all everyday wires have resistance. Even the best conductors have some resistance. And so they use up some of the voltage as we try to push the charges through the circuit. In some devices, like a portable space heater, the friction in the space heater, the electrical friction, or the resistance, is a useful thing. It makes heat where we want it. But in other devices, such as an electric motor, we want to minimize that because that would be wasteful. The motor itself, when it's operating, produces a voltage in the opposite direction that we need to overcome. As it spins, it produces a voltage that opposes what's driving it. We're going to learn about that in one of the later sessions. So that's what the voltage is, what is causing the electrons to go through the circuit. So what are amps all about? What are we measuring with amps? Well, we're measuring the flow of electrons. Well, we could have just said volts times electrons per second. But with all the stuff in our everyday lives, electrons are really tiny. And we have so many of them moving, okay? Let's just take a look at what an amp is. That's 1 amp, okay? 1 amp equals that many electrons passing a point every second in the wire. So those are really big numbers to work with. And in electrical engineering, it's kind of unnecessary to use numbers like that. It would be like going to the grocery store and buying milk by the molecule instead of by the quart, the half gallon, the gallon, the liter, whatever your favorite volume is, rather than molecules. Electrons are tiny, and we move a lot of them in these experiments. In fact, let's go back to that chart. If you even had microamps, a millionth of an amp, you would still have a very large number there to work with. So we will work with amps, okay? That will be the unit that we'll be working with. And remember that volts times amps equals power in watts. So let's do our experiment, we're going to use this multimeter. We call it a multimeter because it measures lots of different things. One of them is voltage, lots of different voltages. So I will connect this wire here to this terminal, and then this other one to the other terminal. One of the things we want to make sure of, let me do a close-up here for you, is that we've got the meter set on a range that's equal to or greater than what the battery's going to put out. If you're not sure, you start with a higher range and work your way down, okay? We don't want it on the 2. This is a 12-volt battery, and it'll produce sometimes as high as 13 volts when it's fully charged. So I have it set on 20. Let's put this on here, and we're going to, there we turn it on. There's that 12.5 volts, pretty reasonable. And the other thing we want to measure are how many electrons are flowing in the wire in amps, okay? Amps are a little trickier. The voltmeter doesn't need a lot of electricity flowing through it. It's sort of like measuring pressure. You could put a little gauge in there and you could measure as high a pressure as you need. But with amps, the electricity has to actually flow through the meter. And if I were to use a meter like this for this experiment and try to push the electrons through here, I would damage this meter. I'd need to get an attachment that bypasses most of the amperage so I don't damage the meter. But actually, I have another meter which will serve that purpose. Looks kind of different. Okay, let me give you a close-up of that. It looks kind of different. What's different is this thing right here opens up. So I don't have to break the circuit to take the measurement. Let's say I have a really thick wire like this. It operates maybe a 100 horsepower or 1,000 horsepower motor, and it needs to keep running, and I don't want to break the circuit and put the meter in there. All I have to do is go like that, okay? And now I can measure it. These are called clamp-on meters. This particular meter measures two kinds of electricity. The kind of electricity that comes out of a battery and the kind of electricity that comes out of the wall. And we'll talk about that kind of electricity later. Okay, so what I'm going to do is I'm going to thread this conductor through here, and we'll turn this on. I'm going to put it on the 400 amp scale because I've done this before, and it's a lot of electrons flowing through here. What I'm going to do now is when I connect the green wire to this terminal, we're going to have a huge amount of electricity flowing through the green wire. This battery is not designed to do what I'm doing. That's why I only let it run for like a second. If I were to do it much longer, I would damage the battery and this wire in my hand would get very hot. It can be dangerous. So you need to know what you're doing. You really shouldn't do this at home unless you have someone with you who has experience working with electricity. Like I said, these batteries are not meant to flow that kind of electricity, but for an instant, they can handle it. All right, what I'm going to do is I'm going to flow the electricity for that second, and I'm going to hit these two hold buttons. What they do is they lock in what is happening at that moment. Okay, and then we'll look at the numbers. All right, you ready? Here we go. Okay. Yeah, it registered just what I wanted. Okay, let's take a close-up of that. And what we have here, is that visible in there? The light's kind of, yeah, 215 amps. And our voltage of the wire dropped to less than 2 volts. Okay? Did that too soon. It dropped to less than 2 volts. There's a decimal there if you look at it carefully, right after the 1. We flowed so much electricity that the voltage dropped. Why did the voltage drop? Well, all sources of electricity have resistance. And so the device itself, like the battery, although it's producing the voltage, if we try to flow too much amperage through it, it uses up its own voltage. And in this case, it used almost over 10 volts of what it's putting out chemically, because we were sending too many electrons through the battery. But that's okay. Our experiment is going to be just fine. So we flowed 215 amps, and we'll just use 2 volts here, okay? About 2 volts of it was going into useful voltage to push them through this wire. That was what we wanted it to do, so that it would move these little guys here. So the wattage that the wire was using up was 2 times 200, 400 watts. It's a lot of watts just to do this, but that's what was happening, 400 watts. At least 10 volts was being dissipated in the battery. 10 times 200 amps, actually more, 215. 10 times that is 2,150 watts dissipated in here. So if I had held that on there for a long time, I would have damaged the battery. Okay? That's why I only keep it on for just a fraction of a second or a second. Now let's focus. I'm not going to focus on the battery because that's a misuse of the battery. But here is this circuit, and we're using up 400 watts to do that. 200 amps to do that. How can we make electricity more practical for making magnetic fields and therefore, say, operating a motor? Because that's what this is. It's a motor that does not drive electricity more practical. Well, one of the things we can do is we can make a loop. Okay? So let's say this loop is about 6 inches in diameter, pretty close. That means the radius is 3 inches. So at 3 inches away from the wire, right here, the strength of the magnetic field is about 3 times, actually it would be pi, 3.141, but we're going to use 3 times more intense than when it's 3 inches away from the wire out here, when this is just stretched out. What we're doing when we make a loop is we're strengthening the wire here, magnetic field here, and we're weakening it out here. Okay? So we tripled it already. Then if I go around twice, for the same number of electrons, I double that. So this is 6 times the magnetic field at 3 inches away from the wire. 6 times stronger magnetic field. Now I have a situation here. I have a device that has 50 turns. Okay? Let's see if you can get a little close up. There's 50 turns here. In fact, you can see how skinny that wire is. There we go. Skinny little wire. There's 50 turns. And let's put this magnet on here. Out of the way. So there's our magnet. And I'm going to energize that coil of wire. But I'm not going to use this big battery. I'm going to use these 2 AA's, which gives us about 3 volts. And of course, internal resistance lowers that a little bit. You saw what internal resistance can do. So let's energize that first. Wow, it's acting almost as good as the 210 amps. Okay? How is that possible? How were we able to move that? Let's measure the amperage, this little battery. Let's measure the amperage. We're going to run that through here. Let's see if that's visible overhead. Yes, it is. Okay. And we'll put the battery in here. And let's turn this to there. And oh, it's the kind of pickup that has. Can you all see that? I don't want it to be too close to the foil. All right, let's energize that and take a look. And we're getting 1.7. There's a decimal between the 1 and the 7. 1.7 amps. 1.7 amps is doing that. How is that possible? Well, those 1.7 amps are going around and around and around 50 times. Let's take a look at what that means. And get the magnet out again. Let's take a look at what it means. Is that visible? And we're going to do the same thing now, but we're going to measure what's going through here. And this machine, this ammeter, doesn't know that there are 50 turns. It just knows all of the electrons that are going through there. So there's 50 times 1.7 amps going through there. And what did we get? Oh, I'm on the wrong range. I'm sorry. That was it overloaded it basically. So let's zero that. Okay, we're on the higher range now. There we go. 96, 95, 94. Battery's running down. 94 amps. You remember what we measured? 1.7 times 50 is 85. Pretty close. Pretty close. So the multiple turns multiplied what the battery is putting out. Okay? So we've got 90. We already got 90, but we're looking for 200 or more. Okay? Remember this? This multiplies it by 3. So 3 times 90 is like 270. So that's why this spins the magnet at least as well as the single wire. We were able to accomplish that by having 50 turns in a loop, in loops. Okay, now when we build electromagnets, we don't normally use wire like this. By that I mean the rubber or plastic insulation. Okay? We don't typically use the rubber or plastic insulation for electromagnets. We use something called magnet wire. There's a whole bunch of different gauges of magnet wire. And get this under the camera. Here's some that's the thickness of your hair. And they get thicker and thicker. I don't have all the possible gauges. There's gauges that might be the thickness of your finger, my finger, little finger, my thumb. It could be different shapes too. They're not all round. For example, here's a special case of magnet wire where it's a sheet. It's a sheet of copper, and it has insulation on it, and this kind of a double insulation here over protecting it. There is a coating on here, I think, but in addition to that, there's just this sheet of special material. So this is a very specialized kind of magnet wire. Typically it's round, but it could have other shapes. Why do we use magnet wire? Well, there's two reasons. One is magnet wire has insulation. Did I say magnet wire is not magnetic? It's not magnetic. We call it magnet wire because we produce electromagnets. It's got very thin insulation. It's heat resistant. But because it has thin insulation, it takes up half the space of wire that has the same amount of metal in it. Let me show you here. You notice that this has exactly the same, diameter wire, but this has really thick insulation. And notice that it takes up twice as much width in that direction, and if I bring it up really close, it's also twice as deep. So 2 times 2 is 4. This takes up 4 times more space than this does. So we can make a far more compact electromagnet with magnet wire than we can with this, and this doesn't withstand heat. So this little coil of wire here, if this was made out of wire with regular plastic or rubber insulation, it would probably be about that big. Okay, so the last thing I want to talk to you about is the speed of electricity. So sometimes electricity is fast, sometimes it's slow. Today we're going to talk about slow. So I want you to imagine a wire about that big around. We're just going to do a thought experiment. Only bulb that's going to light is in your head. Let's take that up a little more. So think of a wire that big around. So here's the inside of that wire. These ping pong balls each represent that many electrons, okay? I also want you to imagine that the electrons that represents, each one, that they're spread along here. It's not just in one spot. They are all along here. So the electrons in here are spread along here. The electrons that this represent are spread along here. The electrons that this represent are spread along there. So remember what this means. It says if that many electrons go past a point in 1 second in a wire, that's an amp. So let's reproduce an amp. You ready? 1001, 1002, 1003. That's how fast this would be an amp. 1001, 1002, 1003. But if I had a wire with lots more electrons in it, remember each of these represents that big number. There's 36 balls in this little can here, this plastic can. And if I took 36 seconds to do that, that would be an amp. Let's do that and see how fast it goes. I'm only going to do 18 seconds and go halfway, okay? 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010, 1011, 2012, 1013, 2014, 1015, 1016, 2017, 2018. So I went through half of them. It would have been all with 36 seconds. That's an amp when I have all these, that many electrons. What's the point? What point am I making? The point I'm making is that even though that's a huge number, the number of electrons that are available in good conductors, like copper, for example, there's so many extra electrons, they don't have to travel very fast in the wire. And when we're doing this experiment with the heavy wire, flowing 200, 250 amps, the electrons are drifting about 6 inches in a minute. In a minute, not in a second, but in a minute. They only go 6 inches in this wire in a minute. If it were a skinnier wire, it would go faster. If it was a thicker wire, they would be going slower. So the electrons move very slowly in good conductors. Next session, we are going to take advantage of what we learned in this session, and that is that if we make a coil, we can really multiply the effect of the electricity, the magnetic field that we produce. And so what we're going to do is we're going to drive magnets using coils, and we're also going to drive coils using magnets. See you then.